Hi, I am Dr. Nancy Wilson, and we're about to start your Organic One lab online. You are going to be doing 5 experiments that are 2 parts each, and the very first one of these is called the distillation of an unknown organic compound. I like starting it with reflecting on one of the readings that's available to you, though it's not required reading, The Art of Organic Chemistry. And in it, it talks about the pieces of a synthetic experiment. So the first part, unfortunately, we don't let you do because that's the part where you decide what reactions and in what order and how much of things you use and size of glassware. So not appropriate while you're learning, though. Too bad because it's actually the really fun part to do that organizing and planning. What you're used to doing is coming in and doing that second part of doing the experiment that we have laid out for you. For synthetic experiments, for the ones you're going to be doing, the first 30 to maybe 60 minutes are all it takes to do the actual synthesis. It's the rest of that first 3 hour period and the whole of the next that gets spent on the third and fourth pieces of this. Because when you do a reaction, it's not as though you pour together 2 compounds and poof, they go 100% into the product you want and you're done. You end up with this huge stew of things, including unreacted starting material, the solvents, the catalysts, side products, and then the thing that you want. So you need to pull that thing you want out from all that rest of the mix. And at the very end, you need to analyze and determine that you have what you think you have and how much of it and how pure. So for this first experiment, what we're going to be doing is we are going to concentrate on those last 2 steps and really the very end of the purification because we'll give you something that is fairly pure and you're going to do a simple distillation on it and then do some further analysis of the distillate that you obtain. The process is going to be very, very similar to what you do in the fourth and fifth experiments, where you do most of the purification and do this last step, which is sort of like a final polish. But it lets us give you experience in doing distillation, which is a very core technique in organic synthesis, and to also get introduced to a couple of the analytical techniques, which will be gas chromatography and IR spectroscopy for this particular compound. The possible unknowns that you could get would be one of these 5 compounds, and they are all clear liquids. They all look completely identical to the naked eye, but they are very different chemically. And we are going to be able to use those differences to identify them in this case, though in general, when we're doing purifications and different steps, a lot of times we're exploiting those differences to pull one thing away from another. And we'll get to that when we get to some more complete syntheses. For now, what we're going to do is a simple distillation, which exploits this characteristics of boiling point. You are going to boil and purify a particular compound. You'll be able to measure that boiling point. You will collect it into a pre-measured graduated cylinder, which will allow you to get a mass and a volume to calculate the density. So you can see from this slide here that already you are going to have some information that most likely by the end of the information you have today, you will know probably what you have. But then we're going to come back in the next lab period and we're going to do 2 more instrumental analyses that will absolutely confirm what you have got. Okay. This process of simple distillation, this is coming out of your lab manual, and this is the setup that you are going to be using. So in the setup, you would be working in a fume hood at all times. You would have a stir plate here at the bottom. And on top of that, you would have this heating mantle, which is sort of like a combination between a bird's nest and a hot, like a heating pad. So this is the way that we heat samples. It is much more safe than using a Bunsen burner, which doesn't have as much control. Plus, many of the things that we use are very volatile, so this is much safer. It would be plugged in through a power controller that is not shown here, but that allows you to control how much of the electricity comes through to the heating mantle to control the level of heat so that you have a lot more fine tuning on the process. in there, which you can't see very well, but this is a round bottom flask, so it's completely round. I'm sort of drawing it out here. What's down in there behind that mantle that you can't see. And that would contain what you're going to distill as well as a magnetic stirring rod. Okay. Attached to that is going to be this three-way adapter. And let me back up a second, that you would clamp and secure this entire setup through the neck of this round bottom flask right here, because this allows you not only to stabilize the whole setup, but to pick it up and away from the heat very quickly in case things went sideways, it started doing things in the flask you didn't like, you could pull it up and away and get it away from the heat. Okay. The three-way adapter will be hooked in through there. Oftentimes we will put on a very heavy grease called stopcock grease onto this joint here. The connections are all ground glass joints that are susceptible to freezing up when they're heated, and especially with certain chemicals. So that stopcock grease prevents that from happening so that you can get them apart easily after the distillation. The three-way adapter will also at the top have a thermometer adapter with a thermometer inserted through. The bulb of the thermometer will be down here below the level of that side arm, and this allows the vapors coming up out of the round bottom flask to kind of wash over it and to get an accurate temperature of the vapors that are coming into the condenser. Something not shown here, you would have something called a Keck clip that snaps on here that keeps that condenser from sliding off during the course of the distillation. The condenser is a center tube shown here, and surrounding it is a jacket that we are going to flow some cool water through. So as the vapors are pushed over here, they encounter this cooled tube. It allows the vapors to condense, and then we collect it out the other side as liquid, and we'll collect it into a graduated cylinder that you have pre-weighed so that we, at the end of it, can weigh the cylinder with the distillate, use the difference to get the mass of the distillate, get the volume of distillate, and calculate its density. The water flowing into the condenser is going to come in through a latex tube that is attached to the water tap. It will always come in at the bottom of these two side arms here. It will go out the top and through another latex tube into the drain. That way, if you put it in the bottom and out at the top, you're filling this entire jacket up before it can exit instead of just sort of dribbling it downhill. So always remember, in at the bottom, out at the top. There are some rules of distillation just to point out. So I mentioned that there is a stir bar in the bottom of this round bottom flask. You would never heat anything without something like a stir bar or boiling stones, because as that solution heats, right where it's pressed up against the hot heating mantle, it's going to start to vaporize, and that can build up, and that bubble that's created will explode out in what we call bumping. So that spills it all over the place, which doesn't do your material very good to lose it that way. It doesn't do the equipment very good either. So if we have something in there to break up that vapor, that prevents it from happening. So the stir bar serves that purpose, as well as when we do syntheses in the rest of the 4 experiments that you do, it is going to help to stir and mix the components. Okay, you never heat a closed system, so I'll just make that note. So we leave this opened up here so that we don't create a buildup of pressure that could break the glassware. The size of the flask would have been chosen so that it's filled about a half to 2/3 full, so not super full, not a huge flask with a little bit of material in it. And as it got distilling, you would distill it so that it would have 1 drop every 1 or 2 seconds. Any faster, you're not doing as good a separation as you could do. Any slower, there is no purpose in putting yourself through that. So you would be adjusting the heat to achieve that. As for knowing where to stop, okay, when you're collecting this in this particular experiment, or when you're collecting a purified substance, you would actually collect the first few drops as what's called a forerun. So you'd collect several drops to take out any low boiling impurities, anything that might be inside that condenser that is getting carried along. And then you'd switch to the container, like this pre-weighed cylinder, to collect the good, pure sample. And you would record the temperature of the first drop going into the cylinder, and you would record again the last drop going into the cylinder before you finished. And then you pull that cylinder out and put the beaker back as everything cooled down and it stopped dripping. As for how to knowing when to stop, you never ever distill to dryness. That is an absolute. So you would be keeping an eye on the level of the substance in the round bottom flask. I usually use that stir bar as a measure. So if the level goes below the level of that stir bar, then you would stop the distillation, even if you didn't have as much as you had been expecting or hoping for. Because if you get a very small amount in that flask, highly heated, there are chemical reactions that you may not want that could go on. So you always want to make sure that you stop the distillation before the flask goes dry. The other way you would know when to stop is if the temperature changed very drastically. So you're going to be watching the temperature on the thermometer as this goes along. Imagine if you had a mixture, which is not the case today, but just imagine, since we're talking distillation, imagine you had a mixture of materials down here in this flask. And the lowest boiling point one has boiled, is vaporized, it's come over, condensed, you've collected it. And when that is all gone, either the temperature is going to drop drastically because the next one is not ready to boil, there are no vapors coming up to change the temperature on the thermometer, so a drastic drop in the temperature tells you that you're done, or the next one's getting ready to boil, and so the temperature will start crawling up and going up to the boiling point of the next compound, so the temperature might spike up drastically. Either one of those, that's a clue that you stop this distillation and that you're done. Okay, so just a quick review on this last slide. So starting up the distillation, you would be adjusting the heat. There's no absolute that we can tell you because every heating mantle and power controller is sort of a unique set. Every compound, if you don't know exactly what you have, you're going to have to watch and slowly ramp it up until it is distilling and make sure it's distilling at that 1 drop per second that you were desiring. You're going to stop the distillation before it goes dry. In the case of this experiment, we usually have you collect about 7 to 10 milliliters, and that's usually no problem without any change because it's fairly pure. You don't see those drops in temperature, but if you were to see one, that would be an indication to turn it off. The very last thing that you would do on this experiment before you finish for the day is you're going to take about a milliliter of that solution, put it into a small vial for gas chromatography analysis, and you would leave that vial to be analyzed between now and the next experiment. And we would provide you with a printout from that analysis. And in the next session, we are going to talk about the gas chromatography analysis, and you would also come back and do the IR analysis. In practice, in the lab, what you would do is then cork that graduated cylinder with a cork that fit very tightly. You would label it because nobody likes mystery chemicals in a drawer. You want to make sure that you label what you've got, the date and your initials, so that it can be tracked down if it were left there. And you would leave that for the next time to do the infrared spectroscopy part of the experiment. So when we come back next time, we will talk about GC and IR and how those analyses are going to add into what you got today. Again, you are going to have a boiling point and be given the mass of the empty cylinder and the cylinder plus distillate. So what you need to get the mass, and you'll be given the volume. So you have what you need to calculate density. For the boiling point, there is one other thing to mention. You're going to compare that to literature boiling points, which are taken at sea level. In Boone, we're not at sea level. Boiling points are lower because the atmospheric pressure is lower. So you're going to need to take what you measured in lab and multiply it by 1.03 so that it would match what it would boil at sea level. So if I had a recorded boiling point of 100 to 103, when I adjusted that, my adjusted boiling point will be 103 to 106. You can double check my math and verify that. Okay. But With those two, you'll probably know what you've got, but we will verify it tomorrow when we come back and do the IR and GC part of the experiment.